All right, so last couple of videos we've been looking at the possible wave nature of light. So today we're going to look at a pretty big experiment that was done. We're going to look at the wave test for light, and this was actually done by a guy named Young in the we're looking like the early 1800s, so like 200 years ago. And of course, this is based on a couple things, and we sort of looked at that last time in the previous video. And the basic idea was, sort of create two sources of light. In order to do that, you have to use Huygens principle. And then to actually create an interference pattern and see if that would actually work or not. So we're actually testing, like, there's a whole bunch of things trying to be tested simultaneously. Does Huygens principle work overall, with point source idea, waves recreating themselves? Does light travel like a wave? If light does travel like a wave, do interference patterns work? Especially the whole light on top of light making black type thing. There's a whole bunch of things all trying to be tested simultaneously. So let's crack out a simulation again and sort of look at what we're talking about. Okay, so this is similar simulation you guys had looked at before, except we got some light coming in. So here we have here's our light source going through an opening, and of course it is going to diffract really well. And we can apply the other ideas. Like right now, the opening is about the same size as the wavelength. So according to Huygens principle, we basically have a little point source in there, so it works really well. If the opening is really small, it still spreads out really good, but most of the energy is being blocked, so it's really weak. And of course, if we make the opening really large, it's curving out the edge, but if we pause especially, you can see the concentration of the energy, the concentration of the waves, the biggest, best waves are definitely going pretty much straight through. And that is that rectangular propagation we've talked about before when they were first studying light and figured light went through like a particle, because light pretty much goes straight through because the openings they were using were just way too big for light waves. It didn't work very well. And of course, Newton explained a little bit of diffraction we get in the sides here from the little bullets hitting these edges and a little ricocheting going on and stuff like that. Okay, so of course we want the openings to be around the same size. So right now this opening is around low 500 nanometers, which is about the wavelength of green light. Now, of course, the idea that they're having is not to use one opening. Okay, we'll turn this off for a second, is to use two openings, something like this. And again, bring the light in. And Huygens principle says we should get a point source here and a point source here. And then the waves should create an interference pattern just like they do with water and sound. And we've looked at that before. So we should get something like this, a nice little interference pattern that spreads out. And of course, this is what they are trying to test for. So we've got a whole bunch of things going on at one time, and this is what they want to try and map out. Okay, so if we sort of laid this out a little bit, okay, the idea is to have some light coming in. We'll use the exact same thing we have in the simulation. And you have a barrier, so we'll draw a little barrier here, something like this. Okay, and then we would have more like point sources being created here, and these point sources are going to create round things, something like this, and this is what they are looking for. So will you get an interference pattern? Okay, is that going to actually happen? Are you going to get maximums and minimums just like we had before? Okay, are you going to have, of course, with maxims, these would be really bright spots, and of course minimums would be dark spots, which is kind of weird to think of with light, but this is what they want to test for. Okay, so that's the basic idea for the simulation. Okay, so of course they go. So again, the simulation gives a simulated type thing. Now, of course, you for detection screen, because these are detection screens, and that's one of the tricky things about this. So we'll pause this for now. Is you can't actually see this. With water, you could actually watch water ripples going on. If it was sound, you could listen to it. Light, you can't. I mean, this is on such a small, crazy level that you can't exactly just watch this happen. So what they would do is at the very end here, they would put photographic plates or light sensitive materials that would actually show where the light actually hit and the intensity of the light. Okay, so if I turn that off, I can bring up a screen. So that's what that little screen represents. So if we would go back to even just the one slit, we'd start with that and have it go through. The light spreads out and it hits the screen on the other side. It will show where it's the brightest really nicely. So you can see it's, which makes sense, is be the brightest in the middle and gets darker on the edges. So that's the idea behind the detection screen. So when they would do stuff like this, they would do the experiment, they would do the setup, they'd have these photographic plates and detection screens, and then after they are done, they could take these detection screens and analyze them like underneath a microscope and stuff like that, or like magnifying glasses or whatever, so they could actually see exactly what was going on and where was the brightest, where's the dimmest, that type of stuff. And you can really see the effect of this when you're changing the slit size opening, the whole D lambda type thing and the intensities and that type of stuff. Okay, so they do the same type of thing with this type of setup. So if we send the light through something like this, if it does the same type of thing, right here should be a bright spot, there should be a bright spot, there should be a bright spot with dark spots in between. So this is the simulated thing of what should happen if it actually worked. And of course, that's the big question, is it going to actually work? Now, it seems kind of weird because right here, you've got dark spot, dark spot. There's light hitting these areas according to the simulation, but you've got crest on trough. The light's actually canceling itself out here and canceling itself out here, and you can't actually see anything, which is really, really strange. So that was one of the big questions. You're going to have light on top of light, and you get black. It's like you take two flashlights, you shine two flashlights on the wall, and you overlap them. Do you have dark spots everywhere? Like, do you have bright spots? No, it just gets brighter. So it's really kind of counterintuitive that this might actually work. But that was the idea behind the experiment. Okay, and this was done by Young like 200 years ago. So let's sort of see what actually came out of this. Okay, so if we actually could see a picture of it, I really like this picture right here. So the simulation showed what it could look like, but if you could actually, you can't actually see it in real life, but if you could actually see it in real life, it would look something like this. We got two light sources, and you can see we got this crazy interference pattern with dark and light spots all over the place. So of course, the big question is, did it actually work? Like, could you actually have Huygens principle applying, making a source of light turn into two equivalent light sources, and then having two light sources shining on the same place? The bright spots make sense. You have brightness all over the place. But actually having two light sources hitting the exact same location and making black. And of course, that was the big question. So let's see what they actually got. So when they actually did the experiment, this will be like more of a modern image, but you actually get something that looks like this. Okay, which means it actually worked. And this one is done with a laser actually, but it's the exact same idea. And you can actually clearly see the interference pattern. Now this was done with, this is two trials. So you got one trial up here and another one down here where they just changed the slits and the orientation and stuff like that a little bit. But it actually worked. Light actually created interference pattern. You can actually easily see the dark spots in between the bright spots. And there's light hitting those sections. There's actual light hitting in each of those areas. There's light hitting here, but it's canceling out. There's light hitting here and canceling out. It's really cool that light is actually hitting at places and actually canceling out. Like you were talking about before, you take two flashlights, you shine them, and you sort of overlap the beams of light. You get a brighter spot on the wall, but it's not twice as bright. It's just a little brighter, because a bunch of the light is actually canceling out other light. Okay, so as the phone rings in the background a little bit there, that's the awesomeness alarm, I guess. So we actually have some really cool things where light is actually canceling off light. And of course, this shocked the snot out of a lot of people. They couldn't believe this thing actually worked. Because remember, it wasn't just about this working. It's proof for Huygens principle. It's proof for light traveling as a wave. It's proof for a whole bunch of things. Light can cancel off light. There's a whole bunch of really, really cool things that come out of this because of this experiment. And it was absolutely amazing. It was really, really neat, but it really locked in the fact that light can actually travel as a wave, because nothing else can create a beautiful symmetrical interference pattern unless it travels as a wave. Okay, so let's get rid of these pictures and get a little room going on here. All right, I'll leave the blue one up there because I really like that picture. So does it create interference pattern? Do you get max and minimums? And of course, like we're talking about, the crazy part is it actually worked, which really surprised a lot of people. So it showed a couple things. First of all, that Huygens principle, that is good to go. Like, there's definitely something there. The idea that waves actually recreate themselves. Okay, that's awesome. That's checking out too. And basically that light actually acts as a wave, okay, creating the interference pattern. So there's a whole bunch of really, really huge things that came out of this. Okay, so it's really, really, really awesome and really neat, and a huge, massive, massive achievement for the wave test for light. This was a really big deal. And there's a whole bunch of other consequences that come out of this actual experiment that was done as well that we will get to later on. But this is a really, really big deal. And in the next video, we'll start looking at some of the math. I know you guys love applying math to everything. And so we'll apply some math to it and sort of see what we can actually find from this.